As Chiara said, I'm going to talk about applications of string theory, and I'm going to focus on two areas. One is applications to QCD, where it already has a stringy object, namely the color electric flux tube between quark and antiquark, and then also applications to superfluids, where the string-like object is the superfluid vortex. So let me start with the QCD part of my talks. This is enormous chalk. I'm not used to it. So, QCD strings and the Lund model. The very origin of string theory was the observation that mesons follow these so-called Regge trajectories, where the mass squared is some slope, alpha prime, times the angular momentum, perhaps plus some intercept. And I'll never get that. Well, I guess I can reach that board. And just to give you an example, if you look at the vector meson rho 770, it has j equals 1, mass equals 770 MeV. That's what this means. And then you've got a spin 3 version of it called the rho 3 at maybe about 1700 MeV. And then there's another one called rho 5 at 2350. And sure enough, if this axis is m squared and this axis is j with 1, 3, 5 as the data points, you can see that things are lining right up. It is a pretty accurate Regge trajectory, and the quark picture is that you've got an up and down bar quark if you're talking about the rho plus, and they're vector mesons, so the spins are aligned. Let's say that's why the rho has spin 1. And then linking the quark and the antiquark, there is a QCD string whose tension is controlled by the parameter alpha prime, which is approximately 1 in the natural units of particle physics, which are, inverse, in this case, GeV squared. Okay, so much for the prehistory of string theory. A bit of history that is still very much with us is the Lund model of meson fragmentation, a space-time picture where we try to build on this idea of mesons as light quarks joined by a string, but instead of considering Regge trajectories where we really have in mind spinning configurations, the Lund model considers a QQ bar pair where the Q and the Q bar are trying to get away from one another. Let's say they start out here, they fly apart, they're light, so their trajectories are nearly null, and a QCD string stretches out between them and sucks away their energy until it's all gone, and then the quark and antiquark abruptly change direction and come back in to a point-like object as illustrated. And if you are most interested in the energy of the quark, as I eventually will be in a heavy ion application, then you might write this very simple energy loss formula for the energy of just the quark. It would be minus the string tension, because as this quark is going out, well, it surrenders energy to the QCD string. But it can get it back when the quark comes back in, so this is not really just an energy loss formula, it's kind of an energy loss or gain formula for the quark. The total energy of the meson, of course, is preserved. Now, the full Lund model is more complicated. I'm scarcely going to need the complications for what I'm going to say later, but let me just briefly indicate that the main message of the Lund model is that sometimes you get a splitting of the world sheet. I better draw it like this. Sometimes you get a splitting of the world sheet, and then what happens next is that these smaller subsystems propagate off in some time-like direction, and this overall space-time picture is the fragmentation of one rather massive meson into two less massive mesons. But within the entire description, you always have the quarks at the endpoints of the string being massless. They carry finite energy, they carry finite momentum, but because they always go along null trajectories, they themselves are massless. All right, so this is old work. This is from the early 80s. It's Anderson with two S's. But what's interesting is that this same mechanism and model is built into Pythia, so it's very much in use today. What I want to do with it is to generalize it in some way to an ADS-CFT setting, and I'm going to derive with some substantial assumptions, as you will see. I'm going to derive an ADS-CFT version of this, which will take the form of energy loss by a light quark in a thermal medium, and it's going to look like this. T is the temperature of the medium, of course. L is going to be the radius of ADS. It can be combined with alpha prime in order to give you a factor of the 't Hooft coupling, as we will review. And you get this rather specific functional form depending on x. And this formula, which is kind of the punchline of the first part of my talk, let's say the first day and a half of my talks, this punchline formula can then be compared to RIC data and LHC data, and with a bit of caveats, which I hope fully disclose when the time comes, there is reasonable fit between this type of formula and the actual data that's coming in from the LHC. So, all right, that's a kind of very broad brush overview. Let me continue by talking about, in general terms, QCD strings as modified in the context of the ADS-CFT correspondence. So in ADS-CFT, of course, we had this wonderful geometry, ADS5, whose metric is L squared over Z squared. How about I write the Euclidean geometry for starters? And this is some solution of type 2b supergravity along with an S5 factor, which I'm going to largely ignore in these lectures. And the boundary of ADS5 is Minkowski space. And the first question we could ask is, how does this geometry accommodate a quark-antiquark pair such as we might be interested in if we're discussing the physics of mesons, whether it be Regge trajectories or the Lund model or something similar. Okay, so how do we get started? Well, the way we get started, as we were taught by Ray and Yi and by Maldacena in 1998, is that we put down some Wilson line. I told you that this is the Euclidean geometry, so I'd better make this boundary R4. And let me suppose that this direction is t, and this direction is z, and the boundary is at z equals 0. And then maybe this direction, we'll call it x. So we'll have a quark as part of our Wilson line, and then an anti-quark, or if you like, a quark going backward in time, and they are separated by distance r. And so we can ask, at the simplest level, what is the potential energy between this quark and anti-quark? That's how we get started. And the way we answer that is to write down some Wilson line operator. This notation means that C is the contour that the quark traverses, so first up this way and then down this way, and W is the Wilson line for that contour, which can be defined as a color trace over a path-ordered exponential. Here is that path-ordered exponential. And another thing I'm going to largely ignore is the physics of the scalars in n equals 4 super Yang-Mills or other holographic theories. I'll write them here so that we just get the idea, but then I'm going to drop them. Since I used x mu already to denote directions in the boundary space-time, let me use y superscript I to denote the adjoint scalars of n equals 4 super Yang-Mills. And then theta is an angle which characterizes, along with the charge of the gauge group, theta is an angle which characterizes what's going on in this Wilson contour. Okay, so we have this Wilson line operator, and then, do we have another board? Yes, I do. And then the prescription for calculating the expectation of this Wilson line is that it is at least approximately equal to the extremum of e to the minus action for a string, with the constraint that the boundary of the string world sheet should be the contour in question. So we just put a note here. Ignore this. And our action, our string action, is nothing more than the area of the world sheet in ADS5. So this metric, capital GMN, is that metric I wrote, the Euclidean metric, for ADS5. All right, so let me get to the punchline of this simplest Wilson line calculation. The picture, I think, is already clear. The point is that we have some minimal surface, which is hanging down into ADS. It looks something like this. It's bounded by construction by the contour C that traces out the trajectory of the quark through space-time. And so we are asked to find the area of this surface sigma. Now, there is a divergence in its area because the geometry gets very big near z equals 0. So you have to do a little trick which is to subtract off from the area of the string, you have to subtract off the area of a single isolated string for the q part of the trajectory and another single isolated string for the q bar part. So with that subtraction in place, what you find is that there's some result V of r times the time over which the quark exists. So let's say this dimension here extends by an amount capital T. So there's this capital T times a potential energy V of r, where V of r equals minus L squared divided by alpha prime 4 pi squared divided by some funny gamma function times 1 over the separation. And L4 over alpha prime squared pardon me, I'm having a moment of hesitation over factors here. L squared over alpha prime equals the square root of the Tufts coupling. Okay, so that's a charming calculation because it shows us how ADS-CFT accommodates a scale-free answer where there is no intrinsic scale in the final answer while allowing a definite length scale for the stringy object. The point is that this length scale alpha prime combines with the radius of ADS to give you this dimensionless quantity, the Tufts coupling, so that you don't have any vestige of confinement. You have a purely Coulombic potential, but it still comes from a string-like object. Okay, questions so far on the basics? Yes?
What was the particle content of the theory of the boundary?
The simplest answer to give you is that this works fine for n equals 4 Cyprian-Mills, where the particle content is a gauge field, 4 Weyl fermions, and 6 real scalars, all in the adjoint of the gauge group.
So those y and i's are real scalars?
Yes. That's right. Right, they're real scalars in the adjoint of SUN, so the trace cares about that adjoint structure, and the path ordering cares about that adjoint structure. Definitely. So like I said, that's the simplest answer I can give you, that this works fine for n equals 4 Cyprian-Mills. For these lectures, I'm not going to look further. I'm going to try to make my best comparison that I can make between n equals 4 Cyprian-Mills and QCD. There's another strategy in this game, which is to modify your holographic construction to bring it closer to QCD physics with some kind of a normalization group flow or better matter content or something or other. And in my experience, for the kind of quantities that I'm going to talk about, this direct sort of naive comparison of n equals 4 to QCD straight away works about as well as more sophisticated treatments. Yes?
Is there a proof for this minimal surface strategy?
Well, I would say this is kind of the core of ADS-CFT, that you say you want a gauge theory quantity, you extremize the corresponding bulk quantity subject to the boundary conditions that there's a match at the boundary. So the same strategy is in place for correlators, where you would say you want a correlator of some local insertions of color singlet operators. you correspondingly extremize the supergravity action subject to boundary conditions on the fields in that action that correspond to the correlator you had in mind. So that's kind of the whole ball of wax. So I would say no, there is not a proof for ADS-CFT. And it's an approximate equality because we understand that really this is only going to work, this extremization procedure is only going to work in the limit of large N, and you might also need a limit of large a 't Hooft coupling to control some kind of stringy worldsheet corrections, which arise here. So in short, yes, it's an approximate equality. Yes, it's sort of the main point of ADS-CFT. No, there is not a proof. Other questions? Those are certainly good ones. Yes?
So there is a possibility of multiple extremum?
Definitely. And so what you're really supposed to be thinking is that extremum is a saddle point approximation to a whole path integral. And so in the case of multiple extrema, the simplest strategy is to use the extremum for which this factor is the largest. And you could try to improve it with, one loop fluctuations and so forth. That would all be fair game, but more sophisticated than I'm going to get. Okay, so where does that leave us? Like I said, we want to compare QCD and n equals 4 super Yang-Mills, hereafter abbreviated SYM, at finite temperature sorry about having used T previously to indicate the extent of Euclidean time. I'm now going to use it only for temperature here. So what is the best way to make this comparison for Wilson loops? Let me advocate the following. First of all, you've got to have, at finite temperature, you've got to have a black hole in ADS. So instead of just ordinary ADS, you have ADS Schwarzschild. However, you still have the same picture for the Wilson loops of a string that dangles from a Q and a Q bar down into the bulk, except exactly what you noted is going to come into play. There will be multiple candidate extrema. This is one, and this is another, where the strings just hang straight down. And at large separation, this one will win, which basically says that screening has become perfect. But at small separations, this one will win, which means that you're going to recover a 1 over r potential at sufficiently small radii. All right, so a little bit more detail is in order simply to say that the metric that we're working with now is a slight modification of ADS5. Here it is, where h equals 1 minus z to the 4th divided by zh to the 4th, and a short computation should convince you that zh is 1 over the quantity pi times T Hawking, which is the same as my temperature T, at least naively. You'll see what I mean by that statement in a moment. Now, it looks like there's a nifty device to handle the boards here. Okay. So what are we going to get when we replay our Wilson loop calculation in this finite temperature geometry? Well, in outline, it's very predictable. You're going to get some potential between quark and antiquark, which is now a function of both r and t. And because it's a conformal field theory, it must be that the answer will be essentially what we got before times some function of the dimensionless quantity r times t. Now, admittedly, I haven't told you what this function f is yet, but that's just a matter of figuring out the details of this particular minimal surface. And I'm not going to give you an explicit answer. I'll just draw on the board some of the main features. All right, so this quark-antiquark potential is something that lattice QCD people study a lot. So we might say, in summary, that they measure VQQ bar, and they usually quote it not in terms of VQQ bar itself, but instead in terms of something they call alpha QQ bar, also a function of r and t, and it's defined as 3/4 r squared times the derivative of VQQ bar times r. So essentially, this is the force between the quark and the antiquark, but the little factor of r squared here is present in order to make it constant for a Coulombic potential. All right, so what do the lattice people actually find? Let me see. I'll try to draw what they find here. Qualitatively, what they must find is a combination of Coulombic behavior, because QCD is almost conformal, some preliminary indications of confinement, because the coupling does run towards larger values at larger separations, and finite temperature screening. So how do those three things come together? They come together about like this. Alpha of QQ bar has values in the vicinity of a fifth. I'll be a little more specific in a moment about exactly the conditions I'm talking about. Let's consider separations on the order of 1/4 of a femtometer, and let's consider temperatures comparable to what you see in a collision at RIC, namely a QCD temperature of something like 250 MeV. Then, under these conditions, what the lattice people say through numerical Monte Carlo is that alpha QQ bar looks something like this. Okay. So yes, you see finite temperature screening at large enough r. It's hard for them to go to really small r, because that means a very fine-grained lattice. It's hard to do. But they can see some sort of rollover of the system trying to confine, and then it says, oh, I'm being defeated by finite temperature, and alpha QQ bar eventually goes down. If you were to assume exactly 0 temperature, then there's an approximate parameterization of alpha QQ bar called based on what's called the Cornell potential. So this is a t = 0 approximation. which has an explicit functional form. Let me not burden you with the details, but just say Cornell potential. Okay, so this is what we're aiming at, and all we want to do, since we are practical people, is we want to pick the parameters of n equals 4 super mills in order to reproduce this as well as we can. That seems a little boring, because of course you can turn dials and knobs and so forth to make one thing match another thing, but you'll see that I have something very specific in mind. I want to set up my parameters so that I can later do calculations and then use the parameters I found to extract numbers. Okay, so what calculation exactly do I have in mind? To do here, just a moment. So I have found that I prefer to compare QCD and super mills at fixed energy density. Rather than fixed temperature. That seems like a bit of a quibble, but in this business of heavy ion collisions, you're worried about the factor of 2 floating around here and there. And what this means, what the QCD temperature, what this equality means for the QCD temperature is that TQCD is approximately equal to 1 divided by the 4th root of 3 times the temperature of super Yang Mills. The reason for this factor of 1 over the 4th root of 3 is that super Yang Mills theory has approximately 3 times the number of degrees of freedom as QCD at this temperature. Okay, so that's step 1, the funny factor of 3. And then the only other thing we've got to play with is the value of the 't Hooft coupling. And the values of the 't Hooft coupling that essentially work are somewhere between about 3.5 and 8. When you pick these values, here's what you get from the super Yang Mills computation. You get some band that's a little bit wider than my chalk is going to be able to draw. Looks about like that. And after a certain point, it drops off to alpha QQ bar exactly equal to 0. So like I said, an unfortunate feature is that in the limit of strong coupling in large N, ADS-CFT tells you that there is perfect screening beyond a certain radius. So we're doing the best we can do. The best we can do is to get this kind of curve from super Yang Mills, which evinces finite temperature screening, but not confinement, because there is no confinement. But we're putting it at a level by choosing, let's say, lambda about 5.5, that's the center band. We're putting it at a level which gives you essentially the same alpha QQ bar. Oh, I should have said, and I choose n equals 3 for super Yang Mills because that's what you have in QCD. Okay, so that's what I wanted to tell you about the setup of making a comparison. And you can see why I wanted to do this. If you remember my formula, I have d dx equals, what was it now? Pi TL squared divided by some alpha prime, I forget there were some other factors here, times 1 plus pi tx squared. Well, there's lots of t's, and there's certainly factors of the 't Hooft coupling in this formula. I've got to have some way of deciding what values to plug into this formula to get the energy loss in GeVs per femtometer. What I'm eventually going to do is exactly what I outlined here. Okay, so I think what I want to do next is tell you gradually how I'm going to derive this formula. But since this is another natural stopping place, let me pause for any more questions. Okay.
What gives this range of lambda? Because there is a error bar in the lattice data, or
I would say this range of lambda is supposed to be representative of the large uncertainties in the comparison. This curve is sloping down, this curve is sloping up. You can make them meet at a point, like a quarter femtometer. That's about where I made them meet with lambda equals 5.5. It's an uncomfortable state of affairs that you can't make them stay close to one another over a substantial range of radii. But I'm an optimist. I would say when we're talking about hard probes of a thermal medium, the kind of energy scale you should be talking about, the kind of length scale you should be talking about, is something like an inverse GeV, which is here. So this is the right range at which to ask for an approximate agreement. And to say that I have something like a factor of 2 uncertainty, I think is representative of the actual comparisons. Fortunately for me, the formulas tend not to be particularly strongly dependent on the 't Hooft coupling because lambda only enters as a square root. Other questions? Yes?
What is the special about this temperature?
This is the temperature which is believed to exist in a collision at the relativistic heavy ion collider out in Long Island. At the LHC, the temperature is, well, of course, it's an evolving temperature, but it's a good 100 MeV higher. Sometimes people quote instead 300 MeV for RIC, 400 MeV for LHC, or it depends. You know, if you want a peak temperature, it's even somewhat higher than that. But this is some kind of average temperature, some typical temperature of the bulk in a heavy ion collision. So if you're going to quote one number in order to do a whole estimate of energy loss through the bulk medium, 250 MeV would not be too far off. Also a good question. Others? Okay. So now what I need to do is to switch gears a little bit back to the ideas of the very beginning of the lecture. You remember how I talked about the Lund model, where the key picture was this one. A quark and an antiquark would fly apart and stretch out a QCD string between them. And then, if they are in fact a bound state, they would come back together again. Now, the interesting thing about this picture is that not all of the energy is in the string. So we might say to ourselves, well, gee, if you want to describe this in string theory in a Minkowskian setting, I need this minus sign that I put here. Your first attempt might be to say, here's our good old Nambu action. The funny thing about it is that this Nambu action only describes some object with spatial extent. It does not describe the point-like objects at the ends of the string. So if you were to derive, for instance, the stress energy tensor of this object, the stress energy tensor would be spread out over the string rather than concentrated in a point-like fashion. This is a key property that's often cited as the reason that string theory is nice, that it spreads things out so as to eliminate ultraviolet divergences. But here is a situation when we seem to need to describe in string theory some localized energy and localized momentum. Localized, I mean at a point. So what had we better do? What I claim is that for trajectories such as these, for classical string motions such as these, at least in the most natural gauge, the proper thing to do is in fact to augment the Nambu action by an extra term. And that extra term is going to be the action for a massless particle at the endpoint of the string. Now, a priori, this seems very funny, especially to experienced string theorists, because a priori, about the only thing you can manage to add at the endpoint of a string is something like a Chan-Paton factor, which has only one factor of x dot. By the way, these dots mean d by d sigma, pardon me, d by d psi. Dots mean d by d psi. Psi is some arbitrary variable which is parameterizing the boundary of the world sheet, and eta of psi is a corresponding metric for that parameterization of the boundary. Anyway, so this term is a nice traditional term for a massless particle. And the funny thing is that I claim in the most natural gauges that you need to include this term in the description of the string physics, the classical string physics. So let me take a few moments to try to justify that claim. And then what I'll do, I think, in my next lecture will be to pursue the consequences of having this term present when we go to more complicated trajectories, let's say in a curved 5-dimensional spacetime, rather than this very simple 1 plus 1-dimensional model. Okay, so the question is, why add finite endpoint momentum? And the way I would come at this, let's say from an elementary perspective, is to look at classical solutions. The equations of motion that you're solving in classical string theory are this simple wave equation on the world sheet, where d plus and d minus are derivatives with respect to tau plus or minus sigma, subject to the constraint that d plus mu is a null vector, and the same is true of d minus x mu. These equations are solved in perfect generality by the following minor but clever trick. This is the beginning of mode expansions for the open string. You pick some function y mu of a single argument, call it psi. This general form already solves the wave equation. It is the most general solution of the wave equation. Push this board up a bit. order to solve those constraints that I wrote at the top of that second board, the Virasoro constraints are called, you have to require that the tangent to this curve y mu must be null. That and precisely that guarantees that the Virasoro constraints will be satisfied. Okay, so now let's take an example. Let's say we've got a string whose boundary follows some elliptical trajectory. So this is the x0 direction, this is the x1 direction, this is the x2 direction. So you see I made it so that the x1 and x2 directions have a curve in them which is elliptical for L1 not equal L2. And then this time coordinate, I had to pick the form that I picked precisely in order that this vector should be null. Okay, so we can kind of get the main idea that I'm driving at just by looking at this example. If L1 equals L2, then we've got a string which is moving as a rigid rod. It's just doing this around its center. But as we take L2 smaller and smaller, the ellipse gets more and more compressed until in the limit, when L2 goes to 0, we get back the kind of string trajectory that the Lund model people were considering. So let's consider that limit. Let's think about that limit a little bit more carefully. What really happens in that limit? And why do we need finite endpoint momentum explicitly to describe it? Well, in this limit, the x2 direction goes away, so let me just write the expressions for x0 and x1. Now, you can, in your own spare time, easily integrate this expression. The integration is slightly complicated by the fact that this is not just a sign, it's the absolute value of a sign because of the square root and so forth. And what you will find is that the world sheet, let's say parameterized by sigma running from 0 to pi and in the space direction and by tau in the time direction, the world sheet maps into space-time in a very funny way. If we divide it up with null trajectories like this, then what you'll find is that a typical snapshot in tau maps onto space-time to look like the following. This is now x1, x0. This snapshot maps partly onto the light cone itself over a finite distance on the light cone, and then it's got some little curvy thing across the main part of space-time, and then it goes back onto the light cone for a finite amount of parameter space. So in other words, this whole region here, this whole wedge and this whole wedge map directly to the light cone. So this maps to the light cone, and this maps to the light cone. You might say that the string is rolling itself up and putting a finite amount of itself right on the light cone. That's the sense in which there's something funny going on in this action, which is most naturally described by adding an extra term, at least in the most natural gauges. I keep saying that because if you insist on a conformal gauge where you can do the treatment that I have just explained, and where the map from the world sheet to space-time is so highly degenerate, in such a gauge, you do not need this extra term. In a conformal gauge, because the world sheet map is so degenerate, this Nambu term by itself will produce finite endpoint momentum. But it's much easier for purposes of most computations that I'm going to do to separate out the part of the string which maps one-to-one into space-time and the part which is a degenerate map. And then the part that is a degenerate map, one can show, gives rise to this massless particle action. All right, let me look at the time. I think I'm starting to run low on time. Another, Chiara, should I do another 5 minutes?
Yeah, but we should allow a little bit of time for the questions.
Okay, well, let's pause here. Are there any questions about this finite momentum stuff? Yes, please.
So if you were to compute scattering amplitudes, would this term ruin, say, the UV finiteness of amplitude?
It cannot, because we're only making some funny gauge choice. Let me put it to you this way. In standard treatments, this is not a funny gauge choice. This is the gauge choice. This is a conformal gauge. There's nothing funny about it, except that for the particular type of solution that I'm talking about, it's a hugely degenerate map of the string into space-time. Despite that, when you actually compute scattering amplitudes, what are you really doing? You are looking at insertions of operators built from the modes of the x mu fields. And if those modes happen to be coherent states which approximate trajectories such as this, you'd never even really know in computations having to do with string scattering. I'm doing classical computations in string theory, and so I really want to know where the string is sort of point by point in space-time, and where its stress energy is. And so a more natural gauge for me is the static gauge. Right. More natural for me is the static gauge, where I would say I am not going to require sigma to run between 0 and pi. It'll start by doing so. I'm going to consider a map from this funny hourglass-shaped region, rather than from a rectangle, into space-time. And so the world sheet parameterization is now funny, but the map is nice. Because now the map can be simply the identity map that x0 equals tau and x1 equals sigma, so that a snapshot of the string will map to the corresponding line segment in space-time. The trouble is that if you want to know what is the energy of this little bit of string, you would have to say that it is the tension, which is 1 divided by 2 pi alpha prime times the length, its instantaneous length, plus twice the energy of one of its endpoints. And it's this quantity which is constant. So this, in other words, this constant quantity, this is the energy, or if you will, the mass of the meson, if we're thinking about the Lund model. And so it's basically this term which you have to account for with that extra boundary term in the string action. Other questions? Yes?
In string theory in general, you have ultra-relativistic strings. The tension is velocity dependent. Should I at all be worried about that in the first term you do not have any velocity dependence? Or in other words, is it clear that this is always an adiabatic process?
First of all, I'm not quite sure I know what you mean when you say that the tension is velocity dependent. Certainly, let's say in the simplest bosonic string theories, you really write down the Nambu equation and you say the tension is the tension, it's a space-time tension. And so if what you're saying is that there's like an effective spatial tension that has a Lorentz factor on it, then I agree. But the space-time tension is just the coefficient of the Nambu term, and that's a constant. Your question about isn't an adiabatic process, that's a good one. Think about it this way. If you're a little piece of string right here, then you'll just continue on your merry way and you don't think anything is happening until all of a sudden the string endpoint rolls up and hits you. And then you're gone. So until you get to this terrible event, you can live your life as a little bit of string quite happily and uneventfully. In other words, this part of the string is perfectly stationary until the endpoint sweeps across it and then makes that part of the string part of itself, part of the endpoint, and it then moves at the speed of light. So there is something very sudden about this, that you're adiabatic, and then you get swept up by the endpoint. Other questions? Yes? I didn't derive it. It can be done. Let me answer you this way. If you start with a Nambu action in conformal gauge, where funny degenerate maps like this are allowed, then you can get from the Nambu action to that Nambu plus particle action. You must, because otherwise you could never recover some equation like this. Yeah. More questions?
Well, I think then we stop here because we have another lecture. We thank our speaker.